So our next speaker is John Mardaljavic, who is Professor of Building Daylight Modelling in the School of Architecture, Building and Civil Engineering at Loughborough University. And today he's going to be talking about daylighting buildings.
Okay, this presentation is not based directly on the paper that's in there. So the paper by Peter Genza and myself is freely available on the LR&T website. We've made it gold open access in perpetuity. I think it makes for a good read. A paper that's a good read doesn't necessarily make a good presentation. And in fact, it was very nearly a paper without any figures at all. In the end, we snuck one in, I think. So I won't attempt to do justice to Peter's part in this presentation. This will be a bit more visual. Beginning with a very early building. This is from where actually my wife was brought up on the island, Lewis, not in that particular dwelling. This is a Stone Age reconstruction of a fairly well-preserved outline. And back then, of course, daylight in buildings wasn't a problem. If it wasn't a concern, there wasn't any at all. You just wanted to get the smoke out. And so there was a few little apertures in there. Certainly that was the case in dwellings in Northern Europe. It's with the great sort of sacred and ceremonial buildings that we first see the deliberate designing for daylight in buildings. Move on a bit. It was really the emergence of glass. This is actually Roman glass, very early Roman window that was actually found in Rome, although there was probably more requirement for it, I think, in Northern Europe. And this street, which is still there in Chester, I think you'll see about 4 centuries of glazing in the different shop fronts and so forth. Move along a little bit, now some streets in Chicago. You're probably lucky to get more than, well, if you found glazing that was more than 4 decades old here. I imagine a lot of the early skyscrapers have had their glazing replaced and so forth. Nearly half of what we see there is glass. Soon as we couldn't rely on the view of sky through a window, and certainly that's the case in places like this, then we needed to determine some sort of measure of daylight. So the history of making measures of daylight goes back some way, and one of the earliest writings that exist, firstly Socrates, this is now 2,500 years ago, that we should allow a design to sort of shield from summer sun when the sun is high in the sky, but then in winter when it's lower down to let sunlight back into a space. And you look at any passive design guide now, and it looks like it was written by Socrates. Not a lot has changed in that regard in 2,500 years. About 500 years later, Vitruvius described what we would now call the no sky line, about how important it was to have visibility of sky. And then Justinian made the distinction between light and view, saying that the view was still important, although if you couldn't see sky, that view was doing something else. It was communicating information about what was happening outside. And fast forward to the 1860s or so, and we start to see attempts to really give a sort of rigorous description of daylight availability, usually in terms of daylight injury. What happens when somebody builds some structure which will lessen the light entering your space? And then the daylight factor. I've got 2 dates there, 1955 and 1895. The 1895 one refers to Alexander Pelham Trotter in the 30s. He made a statement that he first suggested using this relative measure of inside to outside under an overcast condition as a way of rating a space independently of the actually occurring conditions. And in 1955, that refers to the CIE codifying the CIE standard overcast sky as the standard overcast type to use for daylight factor evaluations and so forth. I actually think that in 1955 they drifted away a little bit from that original notion of rating the space independently of the actually occurring conditions. In fact, I do think that was a bit of a misstep. It would have been better, I think, to stick with the original idea, which was a purely uniform sky. About that connectivity to the outside. Now, the daylight factor was actually a very good idea at the time. It's still a useful thing to do now, for sure. It includes the effect of window transmission, reflectivity, and so forth around. And it is about that connectedness to the outside. Now, in 1995, we saw that the emergence of what later on became called climate-based daylight modelling. So now you're using sun and sky conditions which are derived from standardised climate files. Yeah, it's not just the overcast sky now. A feature of the daylight factor, of course, is that it's completely independent of building orientation and climate, locale, and so forth. Whereas climate-based measures, of course, include all of those because you have a location on the Earth and you have the sun moving throughout the whole year. And this is just a very simple space there, showing all the different components of illumination, direct sky, direct sun, indirect sky. So even a very simple space that's illuminated by sun, you have very complex illumination conditions. I'll talk about the case study examples that really caused quite a change. And this one, I think we're still feeling the effect of this change 5 years later. So in 2013, much to a number of people's surprise, and especially me actually, well anyway, I think the Education Funding Agency made CBDM a mandatory requirement for the evaluation of school designs for the building programme, the Priority Schools building programme. This, I think, now is probably about 15 billion because it's been expanded to other programs and so forth. So this really was quite a significant event. It's the first time anywhere in the world where it became a mandatory requirement to do it. So how did that change happen? How does a bit of research really end up in practice? Nobody asked for climate-based daylight modelling. There was no program in the funding, there was no thematic program in any funding body to say we want something like this. It came about simply as an idea. I'd actually spent my previous time doing a bit of postgraduate research in astronomy. I was modelling what gases were doing swirling around some of the most distant objects, and we used to talk about it as being the weather on quasars, quasi-stellar objects, and what was the light like. And I thought, well, if we're doing it trying to model what the light was like for the most distant things in the universe, maybe we should try and sort of model light a little bit more realistically closer to home. So I approached it purely from that sort of what-if perspective. And when climate-based first appeared in 95, I think it's fair to say there wasn't a great deal of enthusiasm generally for it. And it takes a while for things to sort of percolate through. How you get from noodling around with research to something happening in the real world, there are many paths to it, and no one actually tells you what those paths are like, no one delineates them, but most importantly though, there are hidden people along the way, the gatekeepers. These are the ones that you have to convince that this is worthwhile doing. And certainly when it came to the EFA, I had no idea who these gatekeepers were. I didn't even know their name, so I probably would have badgered them if I did know, but back then I didn't. So something happened which made them take this quite sort of bold step. And this goes back to, I think, to the 90s, and I'm trying to fill in gaps here. And actually, I know there's one or two people in the audience who could perhaps, in the question session, help out a little bit here as well. Our school buildings were in a pitiful state. We had a lot of stuff like this from the 70s, which was only meant to be temporary. Of course, it's still being used decades later. And quite rightly, when the Labour government came in 97, they tried to address this and, of course, giving it a snazzy name, Building Schools for the Future. Pretty impossible to build them for any other epoch, but there you go. It's a snazzy name. And when the future did arrive, a number of years later, we had some bright, shiny schools, and indeed it was long overdue. But all wasn't necessarily well. These headlines started appearing in mid-2000, and there was dozens and dozens and dozens of them. Of course, some of them from the usual suspects that will just have a go at anything, but there was a lot of genuine, valid criticism here. And it was quite stinging, this criticism, it really was. The government certainly couldn't ignore its own body, CABE, the Commission for Architecture and the Built Environment, so it didn't ignore them, it just shut them down a few years later. So, what was going wrong? Well, I think what was going wrong was that the message about daylight was actually coming across. It was being taken on by people. Yeah. And so you started to see article after article about health, well-being, light, illumination, productivity, and so forth. The Future Homes Commission study, 63% of people preferred high levels of natural light in homes. So they do what me and my wife did, which is buy a sort of energy catastrophe of a home, a Victorian one, which has great daylight in it, and so forth. But one of the ones that really caught people's attention was this one in 1999. They're putting learning in a good light. This is the Heshong-Mahone study. Claiming quite emphatically improved academic achievement in well-daylit spaces. So what we were seeing was what some people have called instrumentalization of design and architecture. It's now you're not just making a space to be beautiful, aesthetically pleasing, functional. It's about doing good, and really good in very measurable ways. And so this was about improving academic achievement. Now these are all, of course, good things. So designers, perhaps some of them imagine that they were now becoming, to use an expression, the engineers of the human soul. I mean, what they would do would make people's lives better. Anyone familiar with that expression, engineers of human soul, and who first coined it? Actually, it was Joseph Stalin back in 1932. But so once you get an idea like this, and of course it was a lot of this was extremely well intentioned, even though perhaps the science was a little bit shaky, is that you enact on these messages. So the message was being received, but it was poorly implemented. If the only thing that you've got is the daylight factor, then if you want more daylight in a space, that means more daylight factor. And so that's a statement from a BSF document. It says maximize the daylight factor. It didn't say you can just try and get there, then stop. It was just maximize it. Now, if that was the case, classrooms would look like this and would be teaching the kids alongside rows of tomatoes and cucumbers and so forth. So things were going wrong. We look at when things happened. So CBDM back in 1995, it first emerged. The useful daylight illuminance metric was published. A paper in LR&T was one of them in 2005. What was probably one of the first schools that was ever evaluated was 2008. And the FA decision 2013. And then a period I sort of refer to as it certainly felt like the wilderness years, not a lot was going on. Actually, things were happening, although imperceptibly perhaps at the time. There were CIBSE events where this stuff was being talked about, presented. A little bit in the CIE, I think the CIE could do better at being more sort of outward facing. BSI 8206, that revision includes a technical annex which mentions climate-based daylight modelling. That was the school back in 2008. Again, there was no need to do that modelling back then. It was just those architects just wanted to see what would happen. They were game for it. But actually, I think the daylight group was key here, because although I didn't know who those people were in the EFA, the people who did end up advising the EFA were actually people who'd been attending the daylight group sessions. So I think this is where, again, a long-term engagement with professional bodies was probably more a cause of this change than anything else. And so you had people from Arups and Condols and so forth quite regularly attending these events. I would encourage them to carry on doing so. So be prepared for a reaction. And that's quite right and proper. So this article appeared by a colleague in 2014 with a quite emphatic statement here. There's no justification for all of this. Now, this is absolutely perfectly proper. In fact, we don't have enough of this sort of thing, really. And with my sort of associate editor hat on, I would welcome more, certainly correspondence and so forth in LR&T. There are controversial issues around. And if somebody comes up with an idea and you're not too happy about it, then you certainly should, put your name in print about this. Again, I addressed as best as I could the concerns which were brought up in a paper that appeared in CIBSE Technical Symposium a year later. But I think one of the very valid criticisms there was that, not about the methodology, but that the targets, I don't think, in the EFA guidelines are onerous enough, because you can just about pass the criteria for the same fixed design, whether it's facing north, east, south or west. I think if climate-based tells you anything, it's just that those orientations should have different designs. And I think it's because the criteria aren't onerous enough to push you in that regard, but also to encourage multi-aspect lighting wherever possible. Another issue that was brought up was verification. How can we prove this? Now it's a big deal. You have to do this. And so one of the things that was brought up was, well, it's very easy to validate daylight factor measurements. It's almost impossible to validate in the field of climate-based. You need an empty classroom, an undisturbed desk, and leave illuminance meters there for a whole year. And then you've got inter-year variability from climates and so forth. Anyway, it turns out actually that in addressing this criticism, that daylight factor validation is not as straightforward as it seems. You actually need a sky that's got a luminance arc that looks like this, going from the horizon over the zenith and back down to the horizon again. If you were to validate a daylight factor prediction in a real building, you'd need a sky condition like that. Now, if you apply quite a stringent condition, on here it's less than 1% difference between global and diffuse horizontal, you'll end up with sky scans that are absolutely all over the place. And even if you took the average of these, it's still quite different. So the reality is that the real world overcast conditions actually very rarely match CIA overcast skies, which is probably why no one's ever taken this to court, because I think they will get sort of shot down if they tried to sort of defend a daylight factor measurement in a building. It's only if you have 4 vertical illuminance measurements, north, east, south and west, and you have a coefficient of variation between those 4 is just less than 5%, do you actually start to get skies which closely approximate that. So you can't actually measure this and prove by validation a daylight factor. So how is it actually done in practice? Well, when you see what happens is people first check the geometry. Yep. And that's exactly what you do with a climate-based simulation. You check the geometry first. Yeah? You check that the procedures were correctly applied, that the reflectivities and so forth were correct, and also look at the actual modelling approaches. And so people have said, well, quite rightly, there are multiple ways of doing climate-based simulations. There are many ways, many techniques. And so in a recently completed project by Eleonora Brambilla, who's here in the audience, on the applicability of climate-based light modelling, this was an FSLL funded study. It showed actually, as long as you're consistent in your modelling approaches and you best practice, that the different modelling, all the different phase methods, the 2, the 3, the 5 phase, the 4 component and so forth, actually give remarkable agreement. Much more so than you would expect from different thermal models and so forth that are used for compliance purposes. But what about the operational performance of a building? We look at building energy management system. It will record hundreds of channels of temperature. Indoor air quality, CO2. Quite a lot of energy, nothing on the visual performance. Well, nothing in terms of a standardized luminous measurement. Yeah. The ambient light sensors in the light fittings, they're not recording physical measures. We can't use those. So we're not actually recording anything in spaces. We could have notionally well daylit spaces, but if the teachers come in, pull down all the blinds to use the data projectors, it's no longer daylit. The daylight benefit is gone. One or two other quick examples just to show the range of applications. This building, now renamed, it's now called the Central Park Tower. It's not going to be finished till 2020, and it'll be the world's tallest residential building when it's completed in a few years' time. And the legal agreement for the development includes a measure predicted using climate-based daylight modelling. This story began in 2005, and the building that we were concerned about was next door to this very tall tower. It's the Art Student League building, where every great American artist has been associated with this building. And the thing they really valued in this space was the roof-lit studios. They had multiple studios, they were very rare. I think the electric lights was never on, and so they were concerned about the injury. The outline model just showed a huge big tower there, right next to the skylights. So they wanted some basis to carry out their negotiations with the developers to get some compensation for this. They were offered the daylight factor. It was new to them, and they actually thought it was a bit of an abstraction. They didn't really buy into this. They were offered shadow patterns, didn't really go for that. It was north-facing skylights anyhow, so very little sun gets in there. And surprisingly, because not many people were aware of CBDM at the time, they were offered this. And they were asked, well, can we use, well, the person who was advising them asked me, could we use this method? And I said, sure. It's like leaving a light meter on the window, on the skylight, leaving it for a whole year, and every hour totting up the illumination, and then doing the same with the tower in place, and see what the diminution is. So we did the simulations for as is, of course using New York climate data, with a black tower and with a tower 50% reflectance. There's the bottom line number, the annual kilolux hours. There it is with the black tower, with a 50% reflectance tower, and there it is in a table. So down by a third, although that loss was halved by having something reflective. Now that only doesn't need to be the whole tower, of course, just the bit of facade closest to the skylights. Now surprisingly, they wanted this in the legal agreement with the developers, so that when the final design came along, it had to be reevaluated using that technique. And the developers agreed to it. That astonished me. I didn't discover this for a couple of years later. There was the crash in 2008, so things got put on hold. And then in 2013, the design came back, the project came back with a vengeance. And indeed, it caused a lot of fuss because not only was it going to be super tall, it was actually cantilevered over the little building there. So the architectural press went ballistic. There it is in plan, and there's the cantilever. And it was described as this giant boot that's going to stamp down on this poor little building there. So the simulations had to be repeated. There was another huge wad of money put on the table. There was a vote about it. Turned out, actually, it was not significantly worse than what had been agreed to before. Because whilst it was super tall, it was quite a bit skinnier as well. So notwithstanding the cantilever, actually in terms of the light entering the skylights, it wasn't worse than what had been agreed. And so the people voted for this additional 25 million, whatever, dollars and so forth. That's what it looks like a few weeks ago when I took this photo. And this is what it'll look like. And there you can see there's no windows on that part of the facade. That'll be given a sort of zinc oxide metal finish, which should keep its fairly high reflectance of around 50% with weathering and so forth. There are some nice renderings of what these apartments look like, and if you have to ask, you certainly can't afford. Very quickly, conservation. This is doing exactly the same thing really as the New York study, but now looking at exposure of light onto a painting. Now we're concerned about getting too much and we want to reduce it, because this painting, Hambletonian and Mount Stewart, This was work I did with my colleague Stephen Cannon-Brooks, who's sitting over there in the middle. So we modelled this space, ran the simulations using Belfast data now. That's the exposure over the painting, around the sort of 2 to 4 megalux. The conservators would rather it came down to about 600 kilolux. So we investigated first ways of reducing the efficiency of the cupola in reflecting light down, but also the transmission. So we tried this out in simulation first, a mesh, marine mesh over the top of the roof light, and then the National Trust did indeed redecorate the stairway there, and that's being monitored, I think, as we speak. Yes, yeah. I think it's heading in the right direction to get much closer to this value here. Little bit of ancient history in lighting simulation. This was done in the early 90s when we just tinkered around with radiance just to see what it could do. So create this little model, and there's windows above here. And it was to look at the light falling onto the surfaces. Fine. Just what you want, the evenness and so forth. Of course, back then it was pre-CBDM, a static condition. Now, the simulation actually has to predict this before it can deliver this image. It has to determine how much light is falling onto the surfaces before it can simulate the luminance. These were actually the first high dynamic range images. They were simulated ones. This is a high dynamic range image, but now captured with a consumer digital camera, a sequence of about 8 or 10 exposures. And that gets stitched together, and each one of those pixels is a physical measure of brightness. Wouldn't it be nice if we could do in measurement what we can do with simulation? And that's find the light falling onto those surfaces. And with a little bit of smoke and mirrors, we can do that. We can subtract out the electric light. We can treat patches of wallpaper as known reflectors once we've done the photometry on them, which was a little bit tricky with that pattern and so forth, but still did it. And then from that, an image then recreate the prevailing illumination field that's falling onto these surfaces. So in a space like this, just above the door, there would have been one little sensor measuring light. Well, now this is giving us the whole daylight illumination field. And indeed, we've shown that this work that hasn't yet been published, that the accuracy is as good as the standard Hamwell loggers which are being used in the space. And that's work that's going into the daylight management guides that the Trust are revising at the moment. Lastly, a quick word about what sort of buildings do we want to live in. These two in the Dordogne are within a few hundred meters away from each other. This is an absolute catastrophe of a design in energy terms. In a hot place to have virtually 100% glazing. You've got some shading on the inside, but these are black sheets there, so you're not even reflecting the little bit of shortwave maybe that you could do. Yeah. So would we be better off in these climate adapted designs? Well, 200 years ago, for sure. Back then, these were refuges from the outside. People spent all their time outside. They needed that refuge. We don't spend all our time outside, so now we crave highly glazed spaces. And I don't think we should try and go back to these, I think, unless we change our lifestyles and a lot of us take up farming and strawberry picking and whatever when it's seasonal. So we do go for these highly glazed spaces. These introduce problems. Can we fix them technologically? Well, maybe. This is dynamic glazing that varies its tint on a control signal. It can be temperature or illuminance and so forth. And this product, this one varied, I think, from 62% in the clear to 2% when it's fully tinted. Now it goes from 60 down to 1% when it's fully tinted. But you've still got that visual connection with the outside. So, is this the end of daylighting design? Should we just overglaze spaces and fix it afterwards with this? I I think it would be a shame to lose things there, because certainly in low-rise buildings, we should try and make the architecture do as much as possible and be interesting to temper the luminous environment. But where we can't avoid lots of glass, then technologies like this may help. And okay, this is a transit space, really. It's not one where people spend a lot of time. But this one is. So this is our recently refurbished building for our new architecture program at Loughborough University. And we had constant overheating and glare issues with this building. It's about 20 years old. And the glazing was replaced with triple-zoned electrochromic glazing, and does appear to be working quite well. So I think it's one of those rare occasions where maybe there is a bit of a technological fix for bad behaviour, which is just bad behaviour being overglazing everything and so forth. I think I'm just about on time. There's a number of people to be acknowledged in this, but thank you very much.